So let's look at the next lecture then. Into more interesting topics. So those two lectures were really like an introduction to the module, an introduction to the topic of data visualization in general. And now we're going to start the first main subtopic, which is information visualization. So we're going to introduce this idea of information visualization, and we're always going to have lots of examples. You'll see this as a recurring theme in the class. There are lots of examples. And our first main subtopic will be hierarchical data. So this is the overview of the module. The three main subtopics: volume-based, flow-based, and information visualization. And here's what we're going to be talking about for the next few lectures: information visualization. And information visualization is associated with no inherent spatial relations or spatial data. So the data does not normally have, for example, an X, Y, and Z coordinate. It's just some data that's typically stored in a spreadsheet or a database. For example, when you look at your bank statement and you're thinking, do I have any money left in the bank? Is it plus or minus? That data, that list of transactions, has no spatial information in it, right? It's not associated with physical space in any way. So we would call that like information visualization oriented data. And it has an arbitrary number of dimensions. For example, the date you withdrew money or deposited money, where, like who deposited the money or who subtracted the money, who you paid or who paid you, the time, the hour, the minute, the second. It has an arbitrary number of dimensions, and that's what this ND stands for. Arbitrary number. N means arbitrary number, and D means dimensions. So information visualization is associated with abstract data. That's also called abstract data, right, in this module. It has an arbitrary number of dimensions, and because it has no inherent spatial information or is not associated with an X, Y, and Z coordinate, we have to come up with some space to represent that data in. We have to invent a space. We have to create some synthetic visual layout. And that's what this visual metaphor means. We have to come up with something. Like that the rugby glyph was an information visualization. User interaction is very important. And that's one of the recurring themes throughout this module as well. And it separates it from a lot of other uses of the word visualization. If you look in the popular literature, you do see the word visualization. But what makes this class a little bit different from the popular, let's say, media is the user interaction. So really the title of this module should be called Interactive Data Visualization. I'll update that like some year. I don't know which year, but one year. Exploration is very important in this case. So it's in boldface, right? This is the case where you don't know much about your data and you want to just get an overview, find patterns, find trends, find outliers. And this is a main theme inside information visualization, which is exploration. And this is opposed to scientific visualization. Scientific visualization involves spatial data. It involves usually something that occurs in nature, like the depiction of some life form, for example, or the motion of something that's moving, like fluid flow or air flow. It lives in a spatial context, usually a three-dimensional spatial context, usually or four-dimensional. And in this case, there's a very important emphasis on three-dimensional rendering and making it as fast as possible because there's so much data. There's lots of data samples. And analysis is very important there because the data in scientific visualization often comes from some very specialized set of experts, like doctors, for example, generating pictures of your body, or CFD engineers depicting the flow around past a car, for example. So those are specialized people, specialized professions. They already have a hypothesis, like your leg is broken hypothesis. Let's take an x-ray and confirm or refute that hypothesis. And that is the case of analysis. So to confirm or refute a hypothesis. So in information visualization, we spend all of our days thinking about how to represent data in an abstract way. And that is assignment 1. So in assignment 1, you're thinking of 5 different abstractions of data. What are 5 different abstractions? How high can the dimensional data be depicted? Should we use 2D or 3D visual layouts? How can we position or place the data in a space? Should we integrate focus and context? In other words, is some of the data more important and it gets the focus? And is some of the data less important where it just serves as context? So focus is really importance and context is really about not as important, but still relevant for not getting lost. So interaction is also a big theme. So how are we going to interact with our visual layout? Can we change the visualization parameters and the metaphors? Can we move the focus around different areas? Right, this is what you do with your Google Maps, for example. And really, what we are here to do, what we want to educate ourselves in is this topic of large amounts of data, because all of this is kind of easy if you have a small data set. Right? If you have the bank transactions, your own bank transactions for the last week, that's a small data set. We don't really need help understanding that. But what if the data set was all financial transactions of a bank, of one whole bank, over a whole year? Imagine that. If you're the manager of a bank and somebody said, can you show me every financial transaction that has happened associated with this bank, money coming in or leaving for every single customer over this time period of 1 year? That would be challenging. It might, well, the question is it possible and how is it possible? My claim is that yes, it is possible. And I have some ideas on how to do that, but I've already taken this module. But that's what we're here for. We're trying to figure out how do we visualize large data sets. Like what can be done to look at large data sets or big data. And very common strategies for that are selections of subsets, aggregating or putting data into groups with some common characteristic, and extraction of metadata. or derivation of metadata. Does anybody know what that term means, metadata? Name?
Tom.
Tom.
Information describing the data.
That's right, data about data, exactly. Like if I had a set of financial transactions, you might want to know, okay, which bank is associated with those? Like how many of them are there? What's the biggest financial transaction in the data set? What's the average amount of money being passed back and forth and so on? And we are going to start with hierarchical data. So hierarchical data is expressed sometimes using deep hierarchies or large graphs or multimodal data. And we want to look at different kinds of interdependencies or relationships. Like, do some dimensions influence other dimensions? Are they related somehow or not related at all? And overall, one of our goals is pattern finding capabilities. Can we construct some visual design that helps us discover patterns? This is really one of the main objectives. Remember, some of you might remember I said last week that what do we do with data? I said we search. Right? We're always searching. It's not just data, is it? It's kind of like everything. We kind of spend our whole existence searching for stuff, kind of. And searching in data is usually searching for patterns. Like, how can we find patterns? Has anybody ever wondered about the meaning of the word intelligence? Has anybody ever sat around and wondered, like, what does that mean? Something is intelligent, or somebody is intelligent, or something is intelligent, or artificial intelligence. Has anybody ever sat around besides me and wondered, like, what does that word intelligent mean? Or am I the only one? Anybody ever wonder about that? Like, what does that word mean, intelligence? It's really weird. We say some people are more intelligent than others. Anybody have an answer? Like, what did you come to a conclusion? Like, I've concluded that intelligence means this. What's your name? Rob?
Yeah.
Good name.
I define it as like the ability to solve problems, basically. Like intelligence versus knowledge. Like knowledge is just knowing.
The ability to solve a problem. That's a good definition. It does beg another question though. Then you'd have to define problem. Like you'd have to say, okay, now I have to figure out what does problem mean. Did you think about that one?
That's just generic. Anything that needs to
It is a good definition. I like it. Another one?
Yeah, I did come to the definition of it's more like there is no objective intelligence, more it's all relative. So if you take a cow is really, really good at being a cow. But you give it any other task, it's rubbish at it. But in terms of cowness, it's the most intelligent.
I totally agree. And I wasn't thinking of the example of cows. But I was thinking of like, everybody agrees that Einstein is intelligent. Or that's how collectively. But if you took Einstein and put him in the middle of China, he might not be so intelligent anymore, right? He wouldn't know how to say anything to anybody. And it's not just Einstein. I'm just picking Einstein because we all agree he's very intelligent. And so what you just said is intelligence is context sensitive, which is very true. I would agree with that. Why am I babbling on about this? It's because my favorite definition of intelligence is the ability to find patterns. And that does involve the cow, actually, if you think about it. Cows are very good at finding patterns related to like cow survival, cow eating, and reproducibility, and so on, reproductivity. But it generally applies to nature, which has like infinite intelligence compared to a person's mind. So intelligence, you can think of intelligence as the ability to find patterns. It's a useful definition, and it's a thing that we're always thinking about in this module, like pattern finding abilities. Dealing with large amounts of data. So this is what we're here to strain our brains. We want to strain our brains and educate ourselves in how to deal with large data sets, because in assignment 1, you have a very large data set. So it's good to think about ways to handle that. A very common strategy is subsampling. For example, taking every 10th sample and just looking at every 10th sample. That's called downsampling also. Or looking at a very specific subset. For example, one disease, one country, over in 1 year, for example. That's a special subset. We could query the assignment 1 project typo data to get just exactly that small subset. We could apply segmentation techniques. So that's taking the whole thing and then dividing it into different groups that all have something in common. For example, we could take Project Tycho and divide it into different countries. That would be a segmentation of the Project Tycho data. Or divide it into different diseases. That's another segmentation. And then, of course, aggregation techniques. So adding up all the cases of something like malaria in the US in the year 1950, or measles in the US in the year 1960, or something like that. Frequency-based techniques are very common. And that means counting how many times something happens. And the example that you all know is a histogram. For example, how many students scored a distinction on assignment 1? And you get a bar that counts the number of students that got a distinction on assignment 1. And speaking of histograms, there is an example of a histogram. And this is a histogram with directions. So the bars are actually reflecting a vector quantity that's based at the origin. And if there's a vector pointing in this direction, then the size of that bar increases, or the height of the bar increases. So looking here, we can see that there are lots of vectors pointing in this direction, and only maybe 1 pointing in this direction, and 0 pointing in some of the other directions. That's a polar histogram, or a spherical histogram. This is a time series data set, so time is on the x-axis, and amplitude is on the y-axis. Here's an example of a tree map, which we're going to go over in the hierarchical data visualization lectures. These are scientific visualization examples. This is an example of vector field clustering. So this data has been clustered, and all of the vectors inside these clusters have something in common. There's something that's relating them all together to form clusters. That's true about these streamlines too, by the way. These are sort of a set of streamlines, but these are the same set of streamlines that have been clustered. So all these green ones have something in common that makes them different from the other ones. Same with the red and the yellow. And the green ones are fully opaque, and the other ones are transparent. So something is very important. Like that's an example of focus and context as well. Any questions so far on the introduction to information visualization? I have extra copies of assignment 1 and the syllabus. Does anybody need an extra copy of assignment 1 or the syllabus? I'll pass those around just in case. Otherwise, they go into the recycling bin. Can you pass those around? And there were some people at the back that wanted extra copies. Okay, actually, seems like a good time to stop, doesn't it? If it gets too close to the hours, you can let me know. See you at 1700 hours. And in the lab, we have an optional lab today. It's optional.